Testing this out, see how this works. Here's our outline, talking about the six-pack, pitot-static systems, ADC, gyroscopic instruments, the compass, AHRS, HSI, RMI, navigational equipment, anti-ice, de-ice, next steps, and Q&A. All right, so first let's talk about who I am. My name is Monty. I'm a flight instructor, and I founded Emerald Squadron Aviation. My objective is to help you become a pilot. Let's see, moving on. All right, so today we're talking about aircraft. I don't think I can hear myself. Check 1, 2. Yeah, it doesn't sound right. Interesting. Okay, so there's an error with my audio. Okay, how about that? Let's see if that works. So we're talking about aircraft, flight instruments, and navigational equipment. The objective: the student should develop knowledge of the elements related to the operation of flight instruments, as well as the characteristic and operation of navigational equipment. The key elements are the pitot-static errors, the compass correction, and the VOR navigation. If nothing else, I want you to take away those three things. So let's talk about the six-pack. Now, the six-pack gives you three-dimensional information about your aircraft. If we start right there in the middle, the top middle one, that is the... Yeah, it's still not coming through. I wonder if it's just... Oh, interesting. It's only coming through the left ear. Fascinating. Check 1, 2. And check 1, 2. All right, how's this? If I down mix to mono, will that change it? And 1, 2, 3, 4. There it is. Okay, now it's coming through both ears. Awesome. So let's go back to the six-pack. Oh, this is weird. Okay, so today we're talking about the six-pack. Starting from the top middle instrument, that's the attitude indicator that provides the aircraft's nose and wings relative to the horizon, the sky, and the ground. Obviously, the blue is the sky, brown is the ground, angles of bank, and angles of pitch. To the right, we have our altimeter. Below the attitude indicator, we have our heading indicator. To the left, we have our airspeed indicator. On the bottom left corner, the turn coordinator. And the bottom right corner, we have the vertical speed indicator. Now we can split them up into we can split them up into two different categories, and then three subcategories. First category is the pitot-static system, and these all operate under pressure, under the principles of pressure. Then there's the gyroscopic instruments that operate on the principles of a gyroscope, and you can split those two up, gyroscopes, into electric and vacuum driven, and you can split the pitot-static system into pitot-static, or pitot tube, and just the static port. But the short version, let's talk about the pitot-static system. There's the airspeed indicator, vertical speed indicator, and the altimeter, and again, they operate on the principles of air pressure. Now, all three instruments take ambient air from the static port and give you an indication based on air pressure. The airspeed indicator takes ram air and compares it to the static air around the aircraft, the ambient air around the aircraft, and it gives you an indication of how fast you're moving through the air. Now let's review. What are the three pitot-static systems? Or instruments? Yeah, I think that's a better question. That's going to be the airspeed indicator, altimeter, and the vertical speed indicator. By the way, anytime I ask you a question, I want you to actually think about it and try to answer it on your own. Then there's the vertical speed indicator and the altimeter. They're very similar in construction. So you have an outside shell, and then you have an inside aneroid capsule. And on the altimeter, you tell the aneroid capsule what the air pressure is at sea level. Standard pressure is 29.92 inches of mercury. When you pick up the ATIS, you're going to hear the pressure system, or you're going to hear the pressure setting. Set it in the altimeter, and it will compare the inside of this aneroid pressure capsule here to the static air that is pumped, or that is put into this chamber, and it gives you an indication of your altitude. The difference in pressure between in here and out here will tell you your altitude. Now, what the heck is an aneroid? I looked this up. An aneroid is relating to denoting a barometer that measures air pressure by the action of the air in performing the elastic lid of an evacuated box or chamber. Basically, it's a little chamber that helps you determine air pressure. It's a barometer. Now, let's go back to the to this picture here. Now, the vertical speed indicator operates very similar, except that there's the aneroid chamber that gets air from the static port, and then there's a calibrated leak in the outside chamber. And so when the pressure inside the aneroid chamber and the outside casing of the instrument are the same, the pressure is the same, it'll indicate 0, that you're not climbing. Anytime that pressure changes, the static air comes into the chamber and pushes in or expands or contracts based on the air pressure in the bigger chamber. It'll indicate that you are either climbing or descending. Again, based on the difference in pressure. Once the pressure equalizes through that calibrated leak in the chamber or inside the case, it'll go back to 0 once the pressure is equalized. I think it's fascinating. I know it's ancient technology. We're just using air pressure, but that's how the altimeter and the vertical speed indicator both work. Okay, moving on. Let's talk about the vertical speed indicator and altimeter errors. Now, the altimeter errors, you can use the mnemonic device from high to low, look out below, and from low to high, clear the sky. God, I feel gross. Basically, if you are flying your aircraft from an area of high pressure or high temperature without adjusting the altimeter to the correct setting, you will not be at the altitude that you think you are. From high to low, look out below. So from high pressure or high temperature to low pressure or low temperature, you will be lower than what your altimeter is telling you. You will hit the ground earlier than you think. Again, from high to low, look out below. And again, that counts for both pressure and temperature. And the opposite is true. From low to high, clear the sky. If you are moving from a low pressure or low temperature area to a high pressure or high temperature area without adjusting your altimeter, you will be higher physically than what your altimeter is telling you. And of course, the VSI, the errors in the VSI is just, it's delayed. It's not an instantaneous thing. Remember, these are, air pressure. So there is some delay. So don't expect it to be immediate. All right, here's your airspeed indicator. Very similar. It takes static air and then it takes ram air and compares the two. The ram air pushes against this diaphragm, and it gives you an indication of how fast you're moving through the static air around the aircraft. Now let's talk about the air data computer. Now the ADC is a solid state system that takes that pedostatic pressure data and along with some temperature probes, and it calculates your precise airspeed, altitude, vertical speed, and it's displayed on a glass cockpit. Now, what are the 3 pedostatic instruments? Remember, take the time to actually answer this question for yourself so that you're getting something out of this. Now, the 3 pedostatic the pedostatic instruments are the air pressure, the 3 that rely on air pressure. So airspeed indicator, altimeter, and vertical speed. Now, knowing that, what are the 3 gyroscopic instruments? Of course, it's going to be the attitude indicator, the heading indicator, and the turn coordinator. All right. Right now we're just doing a practice live stream for my instrument presentation here. Okay, let's talk about our gyroscopic system. There's the attitude indicator, the heading indicator, and the turn coordinator. And then we're going to talk about the attitude and heading reference system after we talk about those three. Now, the gyroscopic instruments all rely on two basic gyroscopic principles. There's the rigidity in space. A disc that's spinning very fast will be rigid in space. And the second one is precession. Now, a gyro is a small wheel with a weight concentrated on its periphery. As it spins, because it's spinning so fast, it wants to stay where it is. It wants to stay put. And the second principle, precession, if you apply a force to the outer rim of a spinning disc, it will feel that force 90 degrees away in the plane of rotation. So if you try to pitch up on this gyro here, it'll feel a yawing motion. It'll pitch up, but it'll also yaw to the left. And you can actually take a fidget spinner and feel that as you move the gyroscope or move the fidget spinner, in one direction, it'll experience a yaw in a direction 90 degrees away from that input. Now, the two types of gyros you might see are electrical and pneumatic. An electric gyro is, what it sounds like. It's driven by electricity. Now, a pneumatic gyroscope is going to be driven by a vacuum-driven air pump. It's literally high-speed air that turns the gyro, and it spins it super fast. Now, the three instruments here, the turn and slip coordinator, the attitude indicator, and the heading indicator, are all going to operate very similarly. There's a spinning disc inside each of these instruments. Now, the attitude indicator is going to give you information about your nose position relative to the horizon, your wings relative to the horizon, and in terms of angles. So your little triangle here is going to indicate angles of bank. If you turn left 10, 20, 30, 45, or 60 degrees, and if you pitch up or pitch down. Now, in instrument conditions, if you have this instrument working correctly, it makes everything super easy. You just fly your airplane. If your nose is high, you pitch down, put it on the horizon. If your nose is low, pitch it up, put it back on the horizon. Wings are level. If they're banked, you can roll to the right or roll to the left to bank your wings back to level flight. And you can basically fly your airplane. Everything stems from this attitude indicator. Now, the heading indicator is like a top-down view of your aircraft. If your attitude indicator is your forward view or your from the rear looking, the heading indicator is your top-down view, and it gives you an indication of your heading. Now, remember, there are some errors in each of these, and you'll have to be careful and don't just trust them. Don't just assume that they're always right. We'll talk about that in a bit. Now, the turn and slip coordinator is another gyroscopic instrument. This one's electrically driven. The other two are typically vacuum driven. Now, the turn and slip coordinator, you might see two different types. The top one is a turn and slip indicator, and it's not going to have a little airplane. It's going to have a little needle, and it points to a standard rate turn index. This tells you, the standard rate turn tells you that you are banking and you're turning at 3 degrees per second, or a full 360 degree turn in 2 minutes. In instrument conditions, we typically always do standard rate turns. And again, it's a gyro, and so it will have rigidity in space, precession, and it'll have some error as well. So just be aware of it. Yeah. Chaos. Now, the attitude and heading reference system is a solid state system that is meant to replace your traditional gyros. It's a single system that takes solid state sensors, rate gyros, magnetometers, and satellites to give you indications of your pitch, roll, yaw, and your position. Now let's talk about the RMI and the HSI. The RMI has a bearing indicator overlaid on a heading indicator, and it's gyroscopic. So here you're going to have your ADF needle, or your automatic direction finder, and your VOR needle. Now the top of the needles point to the station, and the tails on the VOR points to the radial, or points away from the station and the ADF. Now they both this uses a flux valve. I always think of the flux capacitor, but it's a flux valve. It's a much more precise instrument than your compass. It is based on the principles of electromagnetism. Because a magnetic field produces an electric current, and an electric current also produces a magnetic field, it is essentially three electromagnets that receive lines of electric flux or magnetic flux and they give you a much more precise indication of your heading. And they send that information to the gyro here. Now, your HSI is a horizontal situation indicator. It includes a heading indicator and navigational and glide slope indications. And that flux valve, this right here, the magnetometer, is paired with the gyroscope, and it automatically aligns your heading indicator or your horizontal situation indicator with the magnetic field of the planet. It also gives you, again, navigational information, glide slope. You can bug your heading. Super cool instrument. Now let's talk about the compass. The compass is essentially, it hasn't changed in centuries. It's two small magnets attached to a metal float in compass fluid, and it gives you an indication of your magnetic heading. Now, this aligns with the Earth's magnetic field, and remember that because the Earth is a sphere and we superimpose a grid onto that sphere, a rectangular grid onto that sphere, true north is not co-located with magnetic north. So there will be some error. There will also be error based on your position on the Earth, your acceleration and turning errors, and any magnetic or electrical items inside the aircraft will also induce an error. And we use the acronym UNOS and ANDS to remember those errors. UNOS stands for undershoot north, overshoot south. So if you're flying on a north or south heading and you turn the aircraft, your compass will not indicate correctly. It will undershoot during a turn to the north or from the north, and will overshoot from a turn to the south. In addition, if you're flying on an east or west heading and you accelerate, the compass will erroneously indicate a turn to the north. If you are flying east and west and decelerate, the compass will erroneously indicate a turn to the south. Accelerate north, decelerate south, and of course, there's variation. That's the angular difference between true north and magnetic north. And then deviation, that's any error caused by magnetic or electrical fields inside the aircraft. All right, next let's talk about VORs, navigational equipment. VORs, DMEs, ILS, ADF, and GPS. The VOR is a very high frequency omnidirectional range radio station, and it sends out radios like spokes on a wheel, and they're all in reference to magnetic north. The band for VORs is from 108.0 to 117.95 megahertz, and it relies on line of sight. So if you are behind mountains or if you are on the other side of the planet, the VOR will be useless to you. There are three types of VORs you might encounter. There's a VOR DME, which includes distance measuring equipment, and a VORTAC, which is military tactical air navigation. Now here's our VOR station, right? It sends out radials in all directions. Now what we do is we tune to the frequency stated on the chart and listen to the Morse code identifier. If we hear that Morse code identifier, it tells us the station is active and we can use it for navigation. If we don't hear that, we cannot use the station. Then we're going to go to our indicator and we're going to turn the OBS knob until we either get a to or from indication, depending on what we want to do. In this case, we want to fly to the station, so we have a to indication. Then we turn this knob until the needle is centered with a to indication. Whenever that, whatever that needle ends up pointing to, in this case 030, that's the course that we've selected. Remember, the radial would be the reciprocal. That's 210. That's 180 degrees away from the course we've selected. Radials always point away from the station or from. But this is telling us if we were to fly on a heading of 030 from our current position, we would go directly to the station. So again, the VOR does not care where your nose is pointed. It only tells you your position relative to a course or radial you have selected. So this aircraft could be pointed in any direction, and this instrument would tell you the same information here. In this case, I've put your nose pointed to the station just to make things easy. Now, let's say we dial up that frequency again, listen to the Morse code, and now we have a from indication with 030. We are on the 030 radial away from this station, and it's centered. That tells us that we are on the 030 radial away from the station. Again, the nose can be pointed anywhere. In this case, I just have it set in the same direction just to make things easy. And when you fly, it's probably easiest to turn to the heading that you've selected so that it's easier to visualize what's going on. Let's try another one. let's dial the frequency again, 110.6. We listen to the Morse code. It's active, good to go. Now we're gonna switch. We're gonna turn our needle. In this case, we've selected a 210 to the station, but it's not centered. So if we put our nose on 210, we would be this airplane. We would be the circle in the middle with our nose pointed at 210, and that tells us that the course we have selected is off our left wing. So we have the 210 going to the station, and our nose is pointed in the same direction, and we are not on the line, so the course we've selected is to the aircraft's left. And if we tune to the frequency, listen to the Morse code, and dial it in again, 210, but this time with a right deflection, if our nose is pointed correctly, 210 to the station, then the course would be to our right. Okay. Let's talk about VOR checks. To be legal to fly in IFR, you have to have your Aviates acronym completed, all the inspections. VFR has the Aviates. In IFR, we need that VOR every 30 days. We need to check the VOR every 30 days for it to be legal. And when we do our checks, we can do them at a VOR testing facility at known airborne checkpoints, ground checkpoints, or we can do a dual VOR check if we have 2 VOR receivers in the aircraft. On the ground, you must have better than plus or minus 4 degrees of error. In the air, it's plus or minus 6 degrees. And these are the altitudes that you can receive them at. Yeah. Cool. Let's talk about DME. As we said before, DME stands for Distance Measuring Equipment, and that measures the slant range distance from a station, and it can be used in conjunction with your VOR to determine your position. If you know where you are on a line to the station, that doesn't really help you. But if you know where you are on a line to the station and your distance from the station on that line, you can pinpoint your exact position. This is how it works. The aircraft transmits a pulse to the DME antenna on the ground. The ground receiver responds back to the interrogating aircraft, and the aircraft DME equipment measures the time and converts it to nautical miles, right? Now remember that it is line of sight, so if you are behind mountains or on the other side of the planet, it will not give you a accurate indication. It measures slant range, so it's not very useful when you are really, really high near the station. A general rule is you should be 1 mile away for every 1,000 feet above the station. The greatest error will be when you're directly over the station. It'll only display, it'll essentially give you your altitude in miles, which is not very useful. Okay. All right, so that's the VOR, the DME, and let's talk about the ILS. Actually, we're going to pause it there because I have not completed this presentation. This was just a test of the live stream function. I'm using Streamlabs and YouTube. I don't think anybody's on here, so thank God. But yeah, that was cool. I think not bad. Yeah. And we'll end the stream there.